Hello and welcome to T2 Day 6 of Honors Precalculus. We're going to continue talking about trigonometric identities, but let's warm up by graphing tangent. So in this case, you need to remember that the period of tangent is pi. The period of tangent is pi, but you have this coefficient in front of the x that's in the parentheses, so you take that right there and make it pi over 4 right here. So in this case, when you do that, you get pi times 4 over pi. It cancels, so the period in this case is going to be 4. And then instead of starting at 0, 0, which is kind of where we set the center to be, we know that this 1 is going to move it 1 to the left, and then this 2 is going to move it 2 down because it's negative 2. So instead of being at 0, 0, it'll start right here. So there's like this midline at negative 2. What this 3 is going to do is stretch the amplitude by 3. So usually, tangent usually starts with these 3.0, like that. Instead, it's going to stretch it by 3. So it's going to stretch it up. Instead of going over 1 and up 1, it'll go over 1 and up 3. And you can test all of this by plugging in trig values. So first of all, what this means if we're going to draw the vertical asymptotes is that if we're at the center right here, is at our starting point, and the period is 4, it means we're going to move over 2 and back 2. So if we're here, it means that the first vertical asymptote is going to be right here at x equals 1. And the second one right here is going to be x is equal to negative 3 right here, negative 3. And if you want to track that, you can plug in 1 and negative 3 and see what happens inside the function. It won't be defined. So now, instead of going over 1 and up 1 from the center one, we're going to go over 1 and up 3 up to here, and then it mirrors down to here. Now what you do is you just get a steep curve going down like this and going up like this, and then this curve is going to get replicated every 4. So then if that one's at 1, the next one's going to be at x equals 5 and x equals negative 7. So when you plug in all of the same points repeated every pi, you end up with all of these points, and then you just connect them with the same curve. And now you can copy paste. I'm going to try to freehand it. Let's see how I do. Not bad. So it looks like that. So now let's solve the following equation for all values of x, where x is measured in radians. So we're going to first add 4 and divide by 2. So after we divide by 2, we end up with tangent of that is equal to 7. Now that's not a very, quote, nice trig value. Tangent repeats itself every pi, but it doesn't repeat itself inside the period. It doesn't hit again. So when you do this, you end up with pi over 2 x plus 1 is equal to tan inverse of 7. And there's only 1 in this case. There's only 1. So when you do that on your calculator, you'll end up with 1.429, and it repeats itself every pi. So it's pi n. And then on the other side, you still have pi over 2x plus 1. So you'll use your calculator to get this. And now you're going to divide by pi over 2. And when you do that, you end up with 2n, because the pi will cancel and the 2 gets popped up to the top. And then you subtract 1. So you end up with negative 0.090 plus 2n. There's your answer right there. Those are all of the solutions up there. Now let's get back to trig identities and start simplifying statements. So how do we go about simplifying this one? Well, in this case, we notice that cosine squared is in both. It's to the 4th, but you can pull out the square. So if you factor out cosine squared, you end up with sine squared from the first term, and you end up with cosine squared left in the second one. But this right here, we know, Babylonian identity, is going to be 1. So this is just going to be cosine squared x times 1, which is cosine squared x. So always look for, if you can, see if you can factor things out. In this case, you can factor out a cosine squared x. Now here's where we get to prove what are traditionally kind of like the full identities. What I mean by that is we're going to use identities to prove specific equalities. And here's the key thing. You're transforming one side into the other. Basically, another way you can think about this is taking this and showing that it equals 1. The key thing is you have to start on one side. You can't use both sides. Don't cross over the equal sign. Don't cross over it. So you can't like cross multiply, for example. So in this case, we're going to start on the left and turn it into the right. This one, cosecant by definition is 1 over sine of x. Cosine is just cosine over 1, and tangent is sine x over cosine x. What happens here is you end up with cosines canceling there, and then the sines canceling there, and all you're left with is 1 over 1, which is indeed 1. So a lot of these just collapse really nicely. Sometimes, though, they can be a bit more complicated, and the first choice you have to make is, are you going to try to turn the left side into the right side or the right side into the left? Now, one thing I'm going to tell you is that it's generally easier to combine trig functions with addition than it is to work with multiplication. So in general, if you have to pick sides, pick the one that starts with the plus sign. So let's just start there. Cotangent x plus tangent x. By definition, cotangent is cosine x over sine x, and tangent is sine x over cosine x. These are just by definition right there, identities. Now, if we want to add fractions, if we want to add these fractions, we need a common denominator, which we don't have. So in this case, what we're going to do is multiply this one by sine x over sine x, which is just a fancy form of 1. And we're going to multiply this one by cosine x over cosine x, which is again a fancy form of 1. What you end up with now is you end up with that blue, which is cosine squared x over cosine x sine x, which is our new denominator, plus, and then the green one is just going to be sine squared x over cosine x sine x. And when you add these together, you end up with cosine squared x plus sine squared x all over cosine x sine x. But you might remember this is the Babylonian identity. Sine squared plus cosine squared is 1. So you have 1 over cosine x sine x. And that's the same as 1 over cosine x times 1 over sine of x, like that. The definition of 1 over cosine is secant x, that's the definition, and 1 over sine is cosecant x. And that is exactly what we wanted to prove right there. So we turn the right into the left. So in general, if you have a plus sign, choose that to start with. It's generally easier. Moving on, we have another trig function. In this case, it's a quotient equals tangent. Very exciting. And in this case, it's generally easier to take the bigger thing and reduce it to the smaller one. So let's write all of this in terms of sine and cosine. Cosine is just cosine x, and this is just sine of x over 1. So those are the same two pieces right here and here. Cotangent is defined as cosine over sine, so it's going to be cosine squared x over sine squared x because of this squared right here. Now, how do we multiply this? Well, we can simplify a little bit here, where we know that this sine right here can cancel with this. So you're left with cosine x on top, and then you have cosine squared x all over on the bottom. There's one sine x left. So you're left with, again, this cosine is that one, and there's one sine left after it cancels with that sine. Now, dividing by a fraction is the same thing as multiplying by the reciprocal. So this is going to be cosine x times sine x over cosine squared x. So that's this one right here. The reciprocal is right there. So this cosine, you can think of it as over 1. So what cancels? That cosine cancels with one of the squareds, leaving you with sine x over cosine x. And that's, by definition, tangent x, which is what we wanted to end up with. So in general, if you have bigger or smaller, choose the bigger one and make it smaller. It's generally easier to go in that direction. Again, these just take practice, and they will get smoother and easier as you practice them.